Welcome students, in this session we will discuss characteristic roots and characteristic vectors of a matrix. The eigenvectors of a square matrix are the non-zero vectors that after being multiplied by the matrix remain parallel to the original vector. For each eigenvector, the corresponding eigenvalue is the factor by which the eigenvector is scaled when multiplied by the matrix. The eigenvectors are also called characteristic vectors. Similarly, the eigenvalues are also known as characteristic values. In this session, we first describe the definition of characteristic roots and characteristic vectors. The method of finding characteristic roots will be discussed. Some results related to characteristic roots will be discussed. The method of finding characteristic vectors associated with the characteristic roots will be discussed in the next session, characteristic space of a matrix. Characteristic roots and vectors. Definition: let A be a square matrix over C, the field of complex numbers. A complex number lambda is called a characteristic root or eigenvalue or latent root of a matrix A if there is a non-zero column matrix X such that A into X equal to lambda into X. The column matrix X is said to be characteristic vector or eigenvector or latent vector of the matrix A associated with the characteristic root lambda. Remark: if lambda is a characteristic root of a matrix A, then any column matrix X such that A into X equal to lambda into X is called a characteristic vector of the matrix A associated with the characteristic root lambda. In view of this, zero column matrix can be regarded as a characteristic vector of the matrix A associated with the characteristic root lambda. Definition: if lambda is a characteristic root of a matrix A, then the collection of all the column matrices X such that Ax equal to lambda X is called the characteristic space associated with the lambda. Determination of characteristic roots. Let the non-zero column matrix X be a characteristic vector associated with the characteristic root lambda of a square matrix A, then we have A into X equal to lambda into I into X, where I is the identity matrix of some order as that of the matrix A, that is A minus lambda into I into X equal to 0, the zero column matrix. Since X not equal to 0, the zero matrix, we deduce from the above matrix equation that A minus lambda I is a singular matrix and hence its determinant is 0, that is determinant of A minus lambda I equal to 0, equation 1. The equation determinant A minus lambda I equal to 0, equation 2, is called the characteristic equation of the matrix A. Hence, every characteristic root lambda of a matrix A is a root of its characteristic equation. Conversely, if lambda is any root of the characteristic equation 2, then the matrix equation A minus lambda I into X equal to 0 necessarily possesses a non-trivial solution X, so that X is not equal to 0, the zero column matrix, and A into X equal to lambda into I into X, which is equal to lambda into X. Thus, every root of the characteristic equation of a matrix is a characteristic root of the matrix. If A be n square matrix, then the characteristic equation determined A minus lambda I equal to 0 is an nth degree polynomial equation, so that every n square matrix possesses n characteristic roots, which of course may not be distinct. Also, in this case, determinant of A minus lambda I is a polynomial of degree n and is called a characteristic polynomial of the matrix A. Example 1. Find the eigenvalues of A is equal to 1 1 2 0 2 2 minus 1 1 3. Solution: the characteristic equation is determinant A minus lambda I equal to 0, that is determinant 1 minus lambda 1 2 0 2 minus lambda 2 minus 1 1 3 minus lambda equal to 0, which on simplification yields lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0. By inspection, lambda equal to 1 is an eigenvalue. The other values are obtained as follows: 1 minus 6 11 6 divided by 1 gives 1 minus 5 6, that is 1 minus 5 6 remainder 0. Now, the quadratic equation lambda square minus 5 lambda plus 6 equal to 0 can be written as lambda minus 3 into lambda minus 2 equal to 0, which gives the other eigenvalues lambda equal to 3, lambda equal to 2. Some results associated with the characteristic roots. Theorem 1. If lambda is a characteristic root of A, then k into lambda is a characteristic root of k into matrix A. Proof: if lambda is a characteristic root of A, then there exists a non-zero column matrix X such that A into X equal to lambda into X. Then k into a into x equal to k into a into x, which is equal to k into lambda into x, that is equal to k into lambda into x, showing that k into lambda is a characteristic root of k into a. Example 2, show that the matrix A is equal to matrix minus 1 by 2, 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 minus 1 by 2, 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 minus 1 by 2, 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 minus 1 by 2 is orthogonal. Also find its eigenvalues. Solution. Recall that a matrix A is said to be orthogonal if A into A transpose equal to I, which is equal to A transpose into A. Now, A into A transpose is equal to 1 by 2 into 1 by 2 into matrix minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1 into minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1, which is equal to 1 by 4 into matrix 4 0 0 0 0 4 0 0 0 0 4 0 0 0 0 4, which is equal to 1 by 4 into I, which is equal to I. Similarly, it can be shown that A transpose into A equal to I. Hence, A into A transpose is equal to I, which is equal to A transpose into A, showing that A is orthogonal. For convenience, take B is equal to matrix minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1 1 1 1 1 minus 1. The characteristic equation is determined A minus lambda into I equal to 0. That is determined minus 1 minus lambda 1 1 1 1 minus 1 minus lambda 1 1 1 1 minus 1 minus lambda 1 1 1 1 minus 1 minus lambda equal to 0. Applying R for 3 minus 1, we obtain determined minus 1 minus lambda 1 1 1 1 minus 1 minus lambda 1 1 1 1 minus 1 minus lambda 1 0 0 2 plus lambda minus 2 plus lambda equal to 0. Applying R 3 2 minus 1, we obtain determined minus 1 minus lambda 1 1 1 1 minus 1 minus lambda 1 1 0 2 plus lambda minus of 2 plus lambda 0 0 0 2 plus lambda minus of 2 plus lambda equal to 0. Applying R 2 1 minus 1, we obtain determinant minus 1 minus lambda 1 1 1 2 plus lambda minus of 2 plus lambda 0 0 0 2 plus lambda minus of 2 plus lambda 0 0 0 2 plus lambda minus of 2 plus lambda equal to 0. Yes, 2 plus lambda appears as a common factor in last 3 rows. By the property of determinants, the above becomes 2 plus lambda whole cube into determinant minus 1 minus lambda 1 1 1 1 minus 1 0 0 0 1 minus 1 0 0 0 1 minus 1 equal to 0. That is 2 plus lambda whole cube into minus 1 minus lambda into determinant minus 1 0 0 0 minus 1 0 0 1 minus 1 minus 1 into 1 1 1 1 minus 1 0 0 1 minus 1 equal to 0. That is 2 plus lambda whole cube into minus 1 minus lambda into minus 1 minus 1 into 1 minus 0 minus 1 into minus 1 minus 1, which is equal to 0. That is 2 plus lambda whole cube into 1 plus lambda minus 3 equal to 0. That is 2 plus lambda whole cube into lambda minus 2 equal to 0. Therefore, lambda is equal to minus 2 minus 2 minus 2 2. Since A equal to 1 by 2 into B, by using theorem 1, the eigenvalues are given by 1 minus 1 minus 1 minus 1. Theorem 2, the eigenvalues of a diagonal matrix are the same as its diagonal elements. Proof, let A be the diagonal matrix given by A is equal to matrix A 1 1 0 0 etc 0 0 A 2 2 0 etc 0 0 0 A 3 3 etc 0 0 0 0 etc 0 etc 0 0 0 etc A n n. The characteristic equation of A is given by determinant A minus lambda I equal to 0. That is determinant A 1 1 minus lambda 0 0 etc 0 0 A 2 2 minus lambda 0 etc 0 0 0 A 3 3 minus lambda etc 0 0 0 0 etc 0 etc 0 0 0 etc A n n minus lambda equal to 0. That is A 1 1 minus lambda into A 2 2 minus lambda into A 3 3 minus lambda etc A n n minus lambda equal to 0, which gives lambda is equal to A 1 1, lambda equal to A 2 2, lambda equal to A 3 3 etc. lambda is equal to A n n. Hence, the eigenvalues of a diagonal matrix are precisely the diagonal elements. Proceeding as above, we obtain the following result. Theorem 3, the eigenvalues of a triangular matrix are the same as its diagonal elements. Example 3, Find the eigenvalues of the matrix A is equal to matrix 2 1 0 0 3 1 0 0 H. Solution: the given a triangular matrix, hence applying theorem 3 we obtain that the eigenvalues are 2, 3 and H. Theorem 4: a matrix A and its transpose A transpose have the same characteristic roots. Proof: the characteristic equation of A is given by determine A minus lambda I equal to 0, equation 3, and the characteristic equation of A transpose is given by determine A transpose minus lambda into I equal to 0, equation 4. We know that the determinant of a square matrix B and its transpose are the same. Hence, in particular, the determinant of the matrix A minus lambda I and its transpose A minus lambda I transpose equal to A transpose minus lambda I transpose, which is equal to A transpose minus lambda into I, are the same, which shows that equations 3 and 4 are identical, and hence the characteristic equation of A and A transpose are the same. Hence, the characteristic roots of A and A transpose are the same. Theorem 5: if A and P are square matrices of the same order and if P is invertible, then the matrices A and P inverse into A into P have the same characteristic roots. Proof: take B is equal to P inverse into A into P, then the characteristic equation of B is determined B minus lambda I equal to 0, equation 5, that is determinant of P minus A P minus lambda I equal to 0, that is determinant of P minus A P minus P inverse lambda I P equal to 0, that is determinant of P inverse into A minus lambda I into P equal to 0, that is determinant of P inverse into determinant of A minus lambda I into determinant of P equal to 0, that is determinant of A minus lambda I into determinant of P inverse into determinant of P equal to 0, that is determinant of A minus lambda I into determinant of P inverse into P equal to 0, that is determinant of A minus lambda I into determinant of I equal to 0, that is determinant of A minus lambda into I equal to 0, equation number 6. That is, we have obtained equation 6, which is characteristic equation of A from equation number 5. The characteristic equation of P inverse into A into P, this shows that the matrices A and P inverse into A into P have the same characteristic equation and hence the same characteristic roots. Definition: a matrix A is said to be similar to the matrix B if there is an invertible matrix P such that B is equal to P inverse into A into P. In view of the definition, theorem 5 can be restated as follows. Theorem 6: two similar square matrices of the same order have the same characteristic roots. Corollary 1: if A and B are invertible matrices of the same order, then A into B and B into A have the same characteristic roots. Proof: now A into B is equal to I into A into B, which is equal to B inverse into B into A into B, which is equal to B inverse into B into A into B, equation number 7. Since B is invertible by the definition just above, equation 7 shows that the matrices A into B and B into A are similar. Hence, by theorem 6, A into B and B into A have the same characteristic roots. Corollary 2: if A and B are square matrices of the same order and if A is invertible, then the matrices A inverse into B and B into A inverse have the same characteristic roots. Proof: now A inverse into B equal to A inverse into B into I, which is equal to A inverse into B into A inverse into A, which is equal to A inverse into B into A inverse into A, equation number 8. Since A is invertible, equation 8 shows that the matrices A inverse into B and B into A inverse are similar. Hence, by theorem 6, A inverse into B and B into A inverse have the same characteristic roots. Theorem 7: 0 is a characteristic root of a matrix if and only if the matrix is singular. Proof: the characteristic equation of A is given by determinant of A minus lambda into I equal to 0. 0 is a characteristic root implies there exists a non-zero column matrix X such that A into X equal to 0 into X, which is equal to 0. This implies that the matrix A is singular. Conversely, suppose the matrix A is singular, then A into X equal to 0 has a non-trivial solution, that is there exists a non-zero column matrix X such that A into X equal to 0, which is equal to 0 into X. Hence, 0 is a characteristic root. Corollary: if lambda is a characteristic root of a non-singular matrix, then lambda not equal to 0. Proof: if lambda equal to 0, by theorem 7 the matrix must be singular. Hence, the matrix is non-singular. Hence, lambda cannot be equal to 0. Theorem 8: if lambda is a characteristic root of a non-singular matrix A, then lambda inverse is a characteristic root of A inverse. Proof: since A is non-singular, A inverse exists. Also, By corollary just above, the characteristic root of A must be different from 0, hence lambda not equal to 0, and hence lambda inverse exists. Now, A minus lambda into I is equal to A into I minus lambda into I, which is equal to A into I minus lambda into A inverse, since A into A inverse equal to I, which is equal to A into I minus lambda into A inverse, which is equal to A into lambda inverse into I minus lambda into A inverse, since lambda inverse equal to 1, which is equal to A into lambda inverse into I minus A inverse. That is A minus lambda into I equal to minus lambda into A inverse minus lambda inverse into I, equation number 9. The characteristic equation of A is determinant of A minus lambda into I equal to 0, equation 10. Now, substituting the value of A minus lambda into I given in equation 9, in the characteristic equation 10, we obtain lambda into determinant of A inverse minus lambda inverse into I equal to 0. That is, determinant of A inverse minus lambda inverse into I equal to 0, since lambda not equal to 0 and determinant of A not equal to 0. Now, determinant of A inverse minus lambda inverse into I equal to 0 implies that lambda inverse is the characteristic root of A inverse. Example 4, find the eigenvalues of the matrix A is equal to matrix 1 minus 2 minus 5 4, and hence find the matrix whose eigenvalues are 1 by 6 and minus 1. Solution, the characteristic equation of A is determinant of A minus lambda into I equal to 0, that is determinant of 1 minus lambda minus 2 minus 5 4 minus lambda equal to 0, that is lambda square minus 5 into lambda minus 6 equal to 0, implies lambda plus 1 into lambda minus 6 equal to 0, implies lambda equal to minus 1, lambda equal to 6 are the eigenvalues. Hence, in view of theorem 8, the eigenvalues of A inverse, the inverse of A are minus 1 and 1 by 6, that is the matrix whose eigenvalues are 1 by 6 and minus 1 is A inverse. Now, to determine A inverse, we proceed as follows. Cofactor matrix of A is 4 5 2 1, and hence adjoint matrix of A is matrix 4 2 5 1. Determinant of A is minus 6, hence the inverse of A is A inverse equal to minus 1 by 6 into matrix 4 2 5 1. Theorem 9, the characteristic roots of a Hermitian matrix are all real. Proof, if lambda is a characteristic root of a matrix A, then A into x equal to lambda into x, equation number 11, for some non-zero column matrix X. Now, taking conjugate transpose of the matrix equation in equation 11, we obtain A x star is equal to lambda into x star, that is x star into A star is equal to lambda bar into x star. Equation number 12. As A is Hermitian, A star equal to A, and hence equation 12 can be written as x star into A equal to lambda bar into x star, and hence x star into A into x equal to lambda bar into x star into x, equation 13. Also, pre-multiplying equation 11 by x star, we obtain x star into A into x equal to x star into lambda into x, which is equal to lambda into x star into x, equation number 14. The left hand side of equation 13 and 14 are the same, hence the right hand sides are also same. That is lambda bar into x star into x equal to lambda x star x, and hence lambda bar is equal to lambda, showing that lambda is real. Corollary, the characteristic roots of a skew Hermitian matrix is either 0 or a pure imaginary number. Proof, suppose the matrix A is skew Hermitian, that is I into A is Hermitian. If lambda is a characteristic root of a matrix A, then A into x equal to lambda into x, equation 15, for some non-zero column matrix X. From equation 15, we can write I into A into x equal to I into lambda into x, equation number 16. Equation 16 shows that I into lambda is a characteristic root of the matrix I into A, but I into A is Hermitian, hence by theorem 9 its characteristic roots must be real. Hence, I into lambda must be real, and this is possible if either lambda equal to 0 or lambda is a pure imaginary number. Theorem 10, the absolute value of characteristic roots of a unitary matrix is unity. Solution, if A is a unitary matrix, then we know that A star into A equal to I, where A star is the conjugate transpose of A and I is the identity matrix of the same order as that of A. If lambda is a characteristic root of matrix A, then A into x equal to lambda into x, equation 17, for some non-zero column matrix X. Now, taking conjugate transpose on both sides of equation 17, we obtain A into x star is equal to lambda into x star, or x star into A star equal to lambda bar into x star. Hence, x star into A star into A into x equal to lambda bar into x star into lambda into x, which is equal to lambda bar into lambda into x star into x, equation 18. Since A star into A equal to I, equation 18 can be written as 1 minus lambda bar into lambda into x star into x equal to 0, equation 19. But x is a non-zero matrix and hence x star also is non-zero and hence x star into x not equal to 0. And hence from equation 19 the only possibility is that 1 minus lambda bar into lambda equal to 0 or lambda bar into lambda equal to 1 or modulus of lambda square equal to 1 or mod lambda equal to 1. Since lambda is an arbitrary characteristic root of a matrix A, this shows that the modulus of each characteristic root of a unitary matrix is unity. We now state a result that is useful in solving problems. Theorem 11. The sum of the eigenvalues of a square matrix is equal to the trace of that matrix and the product is equal to the determinant of that matrix. Example 5. If 2 of the eigenvalues of matrix 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3 are 2 and 8, find the determinant of the matrix. Solution. Let lambda be the third eigenvalue. By the previous theorem, sum of the eigenvalues is equal to trace of the matrix. Therefore, 2 plus 8 plus lambda equal to 6 plus 3 plus 3 implies lambda equal to 2. Hence, all eigenvalues of the given matrix are 2 2 8. Again, by the previous theorem, the determinant of the matrix equal to the product of the eigenvalues, which is equal to 2 into 2 into 8, which is equal to 32. Let us summarize this session. In this session, the definition of characteristic roots and characteristic vectors have been given. The method of finding characteristic roots and some results related to characteristic roots have been discussed. Before moving to the next session, try to solve the given questions. Thank you for watching this session. See you next time. Till then, bye.